Problem AT 1033, review for test 2. So we're working on radicals. Our first problem is a perfect square. When you look at the radicand, 100 is a perfect square. You can take the square root, gives us 10. For the variables, with an exponent this high, I would go ahead and divide by the index. The index is 2 on a square root. 2 into 10 goes 5 times. So that's how many groups of 2 you have. So perfect squares. And 2 into 8 will go 4 times. So everything comes out from under the radical on this problem. Our next problem has an index of 3. So we're looking for perfect cubes. This problem actually has perfect cubes. For 125, the cube root is 5, because 5 times 5 times 5 is 125. For the variables, we'll divide the index into the exponent. So 3 into 9 will go 3 times. That would be 3 groups of 3. And 3 into 15 will go 5 times. So everything is able to come out from under the radical. For our next problem, 75 is not a perfect square, so we will break it down to see if there are any squares in it. We will go ahead and use the prime method. So for 75, I think of 3 times 25, and there is actually our square. We'll go ahead and go all the way to primes. And you can write the variables out the same way, or you can just divide. I'll write them out for this one problem. We have 4 x's and 4 y's. When you use the prime method, you make groups for the index because that would give you whatever that power is. So we make groups of 2. When we don't see the index, it's a 2. For every group of 2, that's a square, and 1 can go outside for that group. This is like square root of 25, which is a 5. So 1 5 goes out. The 3 had to stay. It doesn't have anything to go with it to make a square. For your x's, 1 goes out and 1 more goes out. Gives you x squared on the outside. For the y's, 1 more and 1 more. So 2 y's go out, will be y squared. And we put the radical back. We still have the 3 underneath. For your index and the variables, you could have also just divided. 2 into 4 will go 2 times, and that's how many goes out. And 2 into 4 would go 2 times for the y's. For problem 4, 32 is not a perfect square, so we're going to break it down. Also, we have a 3 on the outside, so whatever we take out will multiply by the 3. I'm going to go ahead and use the prime method on 32. So whatever product I think of that multiplies to give 32, I think of 4 times 8, and then I'm going to keep breaking until I have all primes. So this will give me 2's and a 2 times 4, and that 4 will break one more time. And we can write the variables if we want, or we could just divide. Now, we're going to make groups of 2 because the index is 2. That will be a square. So there's 1 2 going out, another 2 going out, 1 x, another x, and a y. All of these will multiply by the 3 that is already on the outside. So there's my 3. I'm taking out a 2 and another 2. 2 x's, which will give me x squared, and 1 y. And then I'm going to put the rest back in. So I have a 2 left underneath, and I have a y left underneath. And now I will need to multiply my numbers. So 3 times 2 is 6, times 2 is 12. X squared y times the square root of 2y. Again, for your variables, if you wanted to just divide by the index is 2. 2 will go into 4 2 times evenly, so both are going on the outside. For the y's, 2 will go into 3 one time with 1 left over. So for the 2, that's the one time it goes evenly, 1 outside for that group, and 1 left over stays underneath. For problem 5, I have a quotient or a fraction form. If I have anything in common between the numerator and the denominator, the 3 and the 27, I can put it back under one radical and simplify first. So I do. 3 goes into 27, so I'm going to put it back under one radical, 3 over 27, and I'm going to reduce. It will stay under the radical, and I will reduce. 3 will go into 3 one time, and 3 into 27 will go 9 times. Now, I can break this radical back apart, put the radical with the numerator and the radical with the denominator, and these are perfect squares. The square root of 1 is 1. The square root of 9 is 3. So 1/3. For problem 6, radical 15 over radical 12, I can also see a common factor between 15 and 12. So I'm going to put it back as one radical and reduce first. These have a common factor of 3, so I'm going to divide by 3. 3 into 15 will go 5, and 3 into 12 will go 4. Now I will break it back apart into 2 radicals, the radical with the numerator and the radical with the denominator. The 4 is a perfect square, so we can take the square root, and there's nothing we can do to simplify the numerator, but it is okay to have a radical in the numerator. So square root of 5 over 2 is simplified form. For problem 7, I don't see anything in common between 3 and 50, so I'm not going to put it back as one radical. And 3 is a prime, so that's not going to simplify. So I'm going to work on this denominator. 50, I can break it down, and we'll see what is in there. So I have 5 times 10, or 25 times 2. And just keep breaking. Right. And now you can take out a 5. This is really your square root of 25. So you are taking a 5 to the outside. The 2 is going to stay underneath. So square root of 3 over 5 times the square root of 2, and we're not allowed to leave this square root of 2 in the denominator. So we want to do what's called rationalize the denominator. We want to make it a perfect square. So the radical is gone. We're not allowed to leave a radical in the denominator. So if we multiply by square root of 2, that will give us square root of 4, which is 2. Or any square root times itself will take the radical off. So we're going to multiply by square root of 2. Now, we can't just do that because we want to, but remember we can always multiply by 1. So if we do square root of 2 over square root of 2, that is a 1. That's okay to do. So now, my 2 square roots will take the 2 out. It's going to multiply by the 5 to give me 10. On the denominator with no radical, and the 3 and 2 will multiply together underneath the radical for the numerator. So we'll get square root of 6 over 10. For problem 8, if we notice the denominator, square root of 16 is a perfect square. We can go ahead and take that square root. It is a 4. The numerator is square root of 15. 15 is kind of large. If you're concerned whether it will break down or not, if you go to primes, you have 3 times 5, and there are not any squares in that. So 15 does not break down. So this is actually our final answer for problem 8. For problem 9, I don't see anything in common between 27 and 80. So I'm going to go ahead and just try to simplify the numerator and the denominator. For the 27, if we break it to primes, and you can do that on the side, 27 gives you 3 3s. It's 3 times 9, and then times another 3. All right? And for 80, we can do 8 times 10, and 8 gives us 2 times 4. 10 is 2 times 5, and then we have 2 2's from the 4. So we can put those all under the radical. So 4 2's and a 5. Right, now let's go ahead and simplify both of these radicals. On the numerator, we can take out 1 3, and that will leave us 3 times the square root of 3. On the denominator, we can take a 2 and another 2. They will multiply together on the outside. So it will be 4 on the outside, and the 5 is going to have to stay underneath. Now, the part that we're not allowed to leave is the square root of 5 underneath. So we're going to have to rationalize that denominator. We will multiply by square root of 5. I'm going to just go down so I have a little bit more room. So I'll recopy what I have. And the square root of 5 is what I want to get rid of. So I'm going to multiply by a square root of 5 over a square root of 5. And on the denominator, I still have my 4. From these, I'm taking out a 5, which is going to give me a 20. And on the numerator, 3 and 5 are not going to simplify, so I will just put them back together. The other 3 will stay on the outside, so 3 times the square root of 15. So my final answer is 3 times the square root of 15 over 20. For problem 10, I see some things in common in the numerator and denominator, so I'm going to put it back as one radical and reduce. So 8p squared over 20p to the 4th. And for the numbers, I have a common factor of 4. So 4 will go into 8 2 times, 4 will go into 25 times. For the p subtract, it will give you p to the negative 2, which makes it go on the denominator. Right, and we're still under the radical. We will break it apart to one radical. I'm going to go this way, so I have a little bit more room. So we'll break it apart and make separate radicals. On the denominator, you can simplify and take the p out for the p squared. So numerator is staying. Can take a p out and leaves the square root of 5. Now, you're not allowed to leave that radical in the denominator. So this is where we're going to rationalize, and we're going to multiply by a square root of 5 to get rid of that radical. Do the same to the numerator, and then we'll simplify. On the numerator, those are just going to multiply underneath to give us square root of 10. On the denominator, for these two, we will pull out a 5 times the p. And that is simplified. For problem 11, hopefully you would notice that there are lots of things in common between these two radicals. So let's put it back together as one radical and reduce. So we have 60 over 15, our x's, and our y's. So to simplify, 15 into 60 will go 4 times. For the x's, subtract, so 6 minus 2 is 4. For the y's, subtract, 12 minus 4 is 8. And there's nothing left in the denominator. So now we have just one radical, and this one is all actually perfect squares. For 4, the square root is a 2. For your variables, divide by the index. 2 into 4 will go 2 times. It goes even. And for the y, 2 into 8 will go 4 times. So this one simplifies without a radical to 2x squared y to the 4th.